The term Internet of Things, or IoT, refers to the concept of devices connected together via the Internet. In the home, these devices can be anything from smart light bulbs to heating controllers or other appliances. The IoT is also commonly used in commercial and industrial applications, such as security, building management systems, environmental monitoring, and factory automation, as well as within the automotive and healthcare industries, and even operating critical infrastructure. The appeal of IoT is that it enables users to interact with, monitor, and control their devices from easy-to-use interfaces such as smartphones or web browsers from anywhere in the world, thanks to the use of embedded processing in the device and internet-based cloud computing. Although the IoT is commonplace, even today it is often insecure, enabling hackers, criminals, or even terrorists to access potentially sensitive data and to potentially be able to control or destroy critical equipment. The purpose of this research was to identify techniques to enable secure, authenticated command and control for IoT devices, and to make building secure IoT systems as easy, or perhaps easier, than building insecure ones. The Secure Remote Update Protocol was introduced in 2016 and builds upon the MQTT protocol, already very widely used for IoT communications. SRUP adds a specification for MQTT messages and defines a standard way for those messages to be used. Although initially designed to provide a way to securely send requests of devices to update their software, the protocol has been expanded to cover all aspects of the command and control for systems of IoT devices. SRUP makes running your own back-end service very easy. Here we see the back-end being run on a Raspberry Pi using a series of Docker containers to provide the MQTT broker and key exchange service. This key service is set up to respond to any requests for identity, although this can be configured to only permit approved devices if required. However, as we'll see, in most cases this isn't necessary. From the device's perspective, an unregistered device will simply connect to the key server and register an identity before moving on to attempt to join a C2 network. The details of the default server for a given backend are provided to the device as part of the registration. Once registered, this registration information will be stored on the device and will be used next time it starts up. MQTT is not an inherently secure protocol. By default, it offers no encryption for message traffic, and brokers are often configured to permit anyone who knows the topic address to publish or subscribe to it, and so to send or receive messages. In SRUP, the containerized backend provides a broker which uses Transport Layer Security, TLS, as used to protect encrypted web traffic, to encrypt the messages. This broker also requires possession of a valid certificate to be able to connect. This certificate limits the topics to which the holder has access, restricting devices to only be able to view messages meant for themselves and only be able to send them on their own or their C2 server's topic. C2 services can be configured to permit any request to join the network. This is not especially secure, however, as in this configuration, nothing would stop an attacker from registering their own device on the network and sending false data to the C2 system. More typically, SRUP devices will be asked to prove their identity by requiring observation. Previous work discusses this in more detail, but the idea here is that an encrypted message is sent to the device containing a 128-bit random number. This must then be shown to an observer who is required to confirm that the value received is the same one securely sent to them via the C2 server. In this example video, all of the devices use a human observer and present the value of the random number as a 4-color pictogram. The C2 system user is required to compare the value shown on the device screen to the one shown by the web interface to the C2 system and confirm that they match. Once devices have joined the C2 network, they may exchange data messages with the C2 server and receive commands to perform actions. In this example, the devices represent a room sensor unit and can send the room temperature and air pressure back to the C2 server, as well as displaying this data, and some other metrics, on the device's screen. They are also capable of controlling external hardware, the state of which can be seen by an icon on the display screen. The system shown thus far is a very simple one, consisting of one back-end system and one C2 server. However, multiple servers can use the same back-end system to belong to the same universe. This enables the C2 network to instruct devices on one network to join another network within the same universe. In this setup, there are two separate networks sharing the same back-end, in this case running on an internet-hosted cloud provider's platform. The C2 for one of these networks is running locally on a desktop computer, and the C2 server for the other is running on a Raspberry Pi. The devices on the ADC2 network represent deployable devices, which can be used together with their own C2 server, or which can be joined to a fixed system, here depicted by the AC2 network. In this example, we can see that devices can be individually tasked to join the new network. This type of setup requires that the two C2 systems share a common back-end, and that the operators of both C2 systems permit the devices in question to have their ownership transferred to the new C2 system. In some scenarios, this won't be the case. For example, one of the systems may operate in a different universe from the other, using a different back-end system, a different set of certificates, and potentially a totally different crypto system. Also, the owners of the devices may not wish to give up ownership of the devices, or perhaps they do not wish to share all of the data from the devices. In order for one C2 network to share a subset of data, and, if they wish, a moderated subset of command actions, with another C2 system, the latest version of the SRUP protocol provides for syndication. In syndication, a C2 server may add a syndication device, and pass the details of another C2 system's backend to this device. The syndication device can then attempt to join that second C2 network and request syndication. In order to do this, both C2 servers need to have access to a shared syndication code to ensure that only authorized syndication is permitted. In this example, this is a static pre-shared key, although the C2 software could easily be modified by developers to use a dynamically generated code. Once syndication has begun, the syndicated C2 server, the one that owns the devices to be shared, will then send a list of device identities that it is prepared to share with the syndicating C2 server, that is the one that has requested the syndication. When the syndicated C2 server receives a data message from its devices, it can be configured to pass this data message on to the syndicating server. In this example, temperature data is being shared, but air pressure data is not. Syndicating servers may also send requests to syndicated servers for actions to be performed. Here, the syndicating C2 system may request that the fan is started or stopped. This is, however, not sent directly to the device in question, but rather to the syndicated C2 server for it to determine if the request will be permitted. Syndicating servers may also send C2 requests to the syndicated server. These C2 requests permit for more complex messages, and could be used for things like requesting that the C2 server applies a software update to its devices, or, as shown here, to request a parameter change for the syndicated devices. The concept of syndication also potentially provides a solution to the problem of how to let a visitor interact with the smart devices in the location that they're in. Rather than having control of these devices be open to anyone, or requiring that the visitor is given full access to the devices, syndication could be used to provide access for a limited time period to a subset of the functionality. So, for example, a house guest could turn on the lights in communal areas or adjust the heating in the room that they're using, but not have access to the security systems or to affect the climate in other parts of the property. Either party to the syndication has the ability to end it at any time. The software shown here, the underlying implementation of the SRUP protocol as a binary library, the Python wrapper for that library, and the example C2 system and device software, as well as all of the key exchange service and associated Docker containers, and a tool to generate the required unique certificates for the backend and any C2 server applications, is all available as open source software and will be made available on the project's GitHub pages. Also, the designs for the custom hat PCB for use with the Raspberry Pi will be made available as well. Further background information about the SRUP protocol and links to papers providing more detail can also be found there.